Hello once again to everyone. You are here at the Athens Sites webinar, Liquid Storage for Wind and Solar Power, Renewable Methanol. As you know, every year, thousands of megawatt hours are curtailed, and this makes wind and solar power less effective from a technical point of view and also less cost effective. So one of the solutions that has been proposed is to channel this power that would otherwise be lost to make renewable methanol. And today we have three experts with us. So Larry Navin from the Methanol Institute, Benedikt Stefanson from Carbon Recycling International, and Juergen Battke from ThyssenKrupp. So now I'll get them to introduce each other in turn, briefly. But before that, I'd like to encourage you to post where you're joining us from. So today I'm moderating this webinar from Addis Ababa in Ethiopia. So please, on the chat box, just write where you're joining from and let us know where you're attending the webinar from. So right, so Juergen, would you like to introduce yourself briefly, just in a couple of words?
Yes, of course. My name is Juergen Battke. I'm Senior Sales Manager for the methanol technologies of ThyssenKrupp. So, and I'm connected directly from my office here in Dortmund, Germany. Hi to everybody.
Excellent. Thank you. Thank you very much. Benedikt, a couple of words to get the listeners acquainted with you.
Yes, thank you. So I'm Benedikt Stefanson. I'm Director for Business Development for Carbon Recycling, and I'm joining you from our headquarters in the Reykjavik capital area in Iceland. And it's a pleasure to be here, and I look forward to talking more about my company and about renewable methanol in general.
Thank you very much, Benedikt. And last but not least, Lawrence.
Hi, Carlos. Thank you. My name is Larry Navin. I am the Director of Government and Public Affairs for Americas Europe for the Methanol Institute, and I am joining you today from the Washington, D.C. area.
Thank you very much, Lawrence. So with a further delay, so let's get the webinar started. So Lawrence, when you have a chance, please share your presentation and we'll get started.
Anybody, are you able to see that, Carlos?
I can see it, but if you go full size on the presentation, it would look better.
All right, here we go.
Perfect, yeah.
Great, thank you. Well, thank you, Carlos, for the introduction. As I mentioned, I'm Larry Navin, Director of Government and Public Affairs from the Methanol Institute. We're pleased to have the opportunity to speak to you today about the many benefits of renewable methanol. First, let me begin with a short overview of the Methanol Institute and who we are. The Methanol Institute was originally formed in 1989 in Washington, D.C. to lobby the U.S. Congress. Now, 30 years later, MI is recognized as the trade association for the global methanol industry. Today, in addition to Washington, D.C., we have offices in Singapore, Brussels, and Beijing. Here on your screen, you'll now see a graphic listing MI's member companies for 2019. As you can see, we represent the world's leading methanol producers, distributors, and technology companies. Here you see a graphic listing an overview of methanol production and demand. Methanol has a number of traditional feedstocks, as you can see, natural gas and coal, and also biomass and renewables, which encompass a large number of potential feedstocks, and which we'll cover in more detail in just a moment. As you can see from this graphic, the roughly 80 million metric tons of methanol that was sold globally in 2018, has a wide array of uses as a chemical building block in pharmaceuticals, electronics, and appliances, to energy and fuel uses, which encompassed over 40% of total 2018 methanol demand. In fact, from 2009 to 2018, direct methanol fuel blending has increased at an annual rate of well over 20%. In 2018, the Methanol Institute decided to commission ATA Insights to produce a report for us on renewable methanol. This report is intended to serve as a primer on renewable methanol and provides a great overview of this increasingly important sector of the methanol industry. Highlights of the report include applications and uses of renewable methanol, information on renewable methanol production, case studies on renewable methanol companies, BioMCN, Enerkem, and Carbon Recycling International, and more. If you've not yet read the report, it is available to download free of charge on the renewable methanol section of our website at www.methanol.org or through the link on the slide on your screen. As I had noted previously, there are numerous pathways available to produce renewable methanol. Feedstocks include agricultural waste. Agricultural waste yields a great deal of biomass that can be converted into biomethanol without interfering with food prices or availability or encroaching on agricultural land. Forestry residues. A large amount of residual biomass, such as leaves, branches, needles, and wood chip, is produced in the process of harvesting trees. These byproducts can be used as a feedstock for producing biochemicals such as renewable methanol. Municipal solid waste. Using municipal solid waste to produce renewable methanol creates value from unrecyclable garbage and relieves pressure on landfill sites. 2/3 of municipal solid waste are either dumped in landfills or incinerated. A significant portion of this waste could be diverted towards producing sustainable chemicals, including renewable methanol. Carbon dioxide. Around 32.5 billion metric tons of CO2 were released into the atmosphere in 2017 alone. With current technology, it is possible to capture CO2 from the atmosphere and from industrial exhaust streams. Power plants, steel and cement factories, and distilleries, among others, produce carbon dioxide that could be used as a source to produce renewable methanol. Lastly, here on this slide, we have renewable hydrogen. Renewable electricity can be used to obtain hydrogen from water by electrolysis. Each of these feedstocks is discussed in greater detail in the report as well. You can see here in the figure shown various renewable methanol production processes, which result from the use of different feedstocks. This slide shows the growing constellation of companies involved either in commercial, renewable, or low carbon methanol production, and also those advancing through the research and development stages of renewable methanol production. And both of those previous graphics, as well as the one I'm showing now, are available in the report as well. This slide, using data supplied by the European Environment Agency, shows the share of greenhouse gas emissions in 2015 arising from each type of transport. As you can see, road transport and maritime are two of the largest categories. Methanol, and by extension renewable methanol, show great potential as both on-road and marine fuels, both for today and the future. As I had noted before, energy and fuel uses already encompass 40% of total methanol demand. You can see in this slide there are already many examples globally of methanol's use as a fuel, both on-road, such as the use of M15, 15% methanol, 85% gasoline, and M100, 100% methanol vehicles in China, and in marine uses, such as the dual-fuel methanol tankers operated by Waterfront Shipping, a subsidiary of MI's member company, Methanex. This slide shows both the current levels of CO2 emissions for a variety of energy and fuel options, and what could be achieved in a green scenario for each option. You can see the already good performance of conventional methanol and the very low CO2 emissions that are possible with renewable methanol. Compared with fossil fuels, renewable methanol reduces carbon emissions by anywhere from 65 to 95%, depending on the feedstock and conversion process. This is one of the highest potential reductions of any fuel currently being developed to displace gasoline and diesel. Additionally, the combustion of pure methanol produces no sulfur oxides, low nitrogen oxides, and no particulate matter emissions. One last thing that I would like to briefly touch on here, and Carlos mentioned this in the opening to the webinar, are the potential synergies available when combining variable renewables and renewable methanol. In recent years, solar, photovoltaic, hydro, and wind have grown to account for a significant part of the energy mix in many parts of the world. These resources provide clean and affordable electricity, but peak yield may not match peak demand. This scenario can lead to wasted energy, as transmission systems operators may disconnect the renewable resource to safeguard the integrity of the electric grid. Instead of being wasted, this electricity could be harnessed to generate clean power or as a renewable fuel for cars and ships. You will learn more about this exciting potential from other speakers later in the webinar. That just about wraps things up for me. You can see here my contact information along with that of my Methanol Institute colleagues, and we'd be happy to answer any questions you have. So please don't hesitate to reach out to us, and thank you again for your time and attention.
Thank you very much, Lawrence, for your presentation. I would like to remind the audience of two things. Firstly, that you can pose your questions in the Q&A box. So sharpen your pencils, and put those questions in. And the other is that if you haven't seen the report already and you want to know more about renewable methanol, you can see the download link in the chat box. So right, so without further ado, then let's go to our second speaker today, Benedikt Stefanson from Carbon Recycling International.
Yes, thank you, Carlos. I'm just going to share my presentation. Okay, now everybody should be seeing the slides. Okay, well, thank you. My name is Benedikt Stefanson. I'm the Director of Business Development for Carbon Recycling here in Iceland, as I mentioned earlier. On this first slide, you can see a picture of our production plant in the background, which we'll, of course, talk about in more detail in a moment. And in the foreground is a car which drives on 100% methanol as well as gasoline. Developed by the Chinese automaker Geely, which is also an investor in our company. I like the phrase "to eat your own dog food," meaning when we started out, there was a lot of doubt, especially here in our local community, about that methanol is really a mainstream fuel ready for prime time. We've now been driving these cars for almost 3 years and with no issues. Using, of course, the existing infrastructure to distribute the methanol. This is a small fleet, though, I should mention, and most of the use of our product actually is in blending gasoline or in production of biodiesel. Let me give you a brief overview of our company. So we were launched in 2006 here in Iceland by a group of 4 entrepreneurs. We have been equity financed, private equity financed from the very beginning by investors in the beginning, mainly from Iceland and the US. And in fact, our production plant was financed mainly within the Icelandic community. And then later on, Methanex from Canada and Geely from China have joined the group of investors, sort of a strategic investors with looking at the long-run potential of methanol, both as a chemical and fuel, as a green chemical and green fuel. We built and own and operate this first industrial scale methanol plant, renewable methanol plant, as we should probably call it in the context of this presentation or this seminar. But I also like to refer to it simply as CO2 to methanol because, as I will touch on a bit later, the same technology can use any source of hydrogen. We have been marketing this product from this production plant worldwide since 2012 under our own brand name, Volcanol, which derives from the fact that we are located here in a volcanic country, and both the electricity and the CO2 source are related to volcanic activity. We therefore have developed the technology and implemented it commercially, and we are now offering this to the world on basically as a turnkey provider, an EPCM essentially. And our team, because we've been working on all of these different topics, obviously the research and development of the technology, finding the right business model for selling this type of technology and solution, as well as advocating for this type of process to make renewable fuels, as opposed, for example, of biofuels. And now, as I mentioned, we have a very experienced team that is ready to deploy these systems at a much larger scale. So we cover the full value chain. Now, what it is that we have developed? So this is a very simple schematic to explain the general idea. To make renewable methanol or to make methanol from CO2, we need essentially two front-end modules. One that takes a flue gas source of any kind and purifies the CO2 stream from that source. A second module which generates the hydrogen. In this picture, we are representing electrolysis, which is essentially what gives the name to the product as renewable methanol, from renewable energy, that is. And then what we're of course looking for are very low carbon intensity energy sources, so wind, solar energy, hydro energy, and here in some countries, as in Iceland, also geothermal activity. We then have developed the conversion system, which takes in one step the CO2 pure, hydrogen pure, and converts it into the molecule methanol, which is identical to the methanol that is produced by basically any methanol plant in the world. And downstream, therefore, it can enter into any of the existing infrastructure. As Lawrence mentioned, about 70 to 80% of the methanol produced in the world goes into some kind of chemicals production, but more and more it is also going into transport applications. I've also represented here on the slide the basic mass balances. So as you can see, we need for 1 ton of methanol approximately 200 kilograms of hydrogen, and approximately 1.4 to 1.5 tons of CO2. Now, as I mentioned earlier, the hydrogen could also be coming as a byproduct from another process. In that case, you often end up with a diverse stream of gases where you have to extract the pure hydrogen, and then you have exactly the same downstream process. So in the European Union, this has now begun giving a particular name. The EU is going to allow this type of process to be competitive with biofuels and fuel from electrolysis, and calling them recycled carbon fuels. This is a picture of the plant that I mentioned earlier that is already in operation since 2012 here in Iceland. We named it after George Olah, the famous chemist who won the Nobel Prize in chemistry, and also wrote a book right around the same time as we were launching the company called The Methanol Economy, in which he describes essentially how methanol can be an essential carrier for energy, both as a chemical feedstock and also as a fuel. The first commissioning of this plant was in 2012. We upgraded it in 2015 from 4 to 12 tons per day. And it now has a nameplate capacity of 4,000 tons per year and converts, therefore, about 5,600 tons of CO2 for that production. We have baseload electrolysis of 6 megawatts in this plant to give you an idea of the energy intensity. In the background, you can see a geothermal power plant that is the source of the CO2 in this case. The volcanic activity is the source of the CO2. But as I was describing in the earlier diagram, this technology, of course, works with any source of CO2. So we have gone from essentially developing this at a very small lab scale until we financed and implemented the industrial scale plant in 2012, then upgraded it in 2015. Currently, we're working on projects in Europe, which are actually of a smaller vintage, projects where you will only produce approximately 1 ton per day, but they are to demonstrate that we can operate this type of chemical plant with intermittent wind power as well as a totally different stream of energy from the steel gas, blast dominant furnace gases. And these two projects are going to be implemented in 2019 and 2020, one in Germany and the other one in Sweden. Now, why is this process considered to be low carbon intensity or carbon neutral? We have to, of course, think about this in the context of what we're doing today, the business as usual, in which we have a lot of industry that emits CO2 into the atmosphere. We rely in our transport system for 99% of the energy on oil-derived products. And so the oil industry has its own upstream emissions, and of course this carbon from the earth is then combusted in the vehicles and emitted into the atmosphere and enters as a net addition. Now, if we then do this instead with our process, we can take that CO2 that would otherwise have been emitted by the industrial emitter, convert that into a alcohol, the methanol, utilizing low carbon intensity or zero carbon intensity energy sources. And although the vehicles that use the CO2 are combusting it, we have essentially created a net reduction in CO2 net emissions for the system. So putting this more into a numerical values, according to, for example, here in Europe, European regulation, we should compare what we are doing, our pathway, with the baseline, which is gasoline or diesel. And in that case, if we convert everything into tons of oil equivalent, we would be reducing the carbon intensity by up to 4 tons of CO2 per ton of oil equivalent. And in chemicals, we are essentially sequestering the CO2, and we have a similar or even larger reduction depending on what comparator you use. I wanted to end up by basically giving you a quick overview of how we think about the economics of this and the economic drivers behind this technology. So obviously we are transforming an energy source into another energy carrier, that is the methanol. So everything is driven by the price of the energy source, the price of the hydrogen essentially. Here, what I'm showing you is essentially what we saw as the product value in the last year or so, which is the blue region on this larger diagram, larger graph. The line that goes diagonally up from the left to the right is essentially representing the full conversion cost of the underlying electricity into the product. So it's the transformation and the other operating costs. And so what is above that diagonal line is basically the returns that can be accrued to capital. And so on the right-hand side, I'm showing you basically where we're deriving the product value from. That is the green premium that is embedded in current biofuels, and which then drives the value to the buyer. And the lower diagram on the right-hand side shows you electricity prices going forward for the next 5 years in the Nordic region, which kind of represents the largest supplier of renewable electricity today in the Nordic countries, Norway, Sweden, and Denmark. And we can see that after basically a spike in electricity prices last year, they're now trending back to about 30 to 32 euros per megawatt hour. And that is what is giving us that value on the diagram that I'm showing you of production costs of 42 cents euro cents per liter of methanol, and a product value that is well above that, basically looking at last year. So what we're seeing basically is that we can push down the cost of production, both in terms of CapEx and also by increasing efficiency in the process, that especially here in the European market, we'll be increasing targets for low carbon intensity fuels, a cap on crop-based biofuels, basically increasing the demand for these new processes, and that other alternative solutions, especially in transport, such as battery-operated vehicles, are limited to light duty and low range. So we see a lot of demand continuing for liquid renewable fuels. And also energy prices should be coming down. The levelized costs of wind and photovoltaic are falling. Intermittency basically means that you have to invest in overcapacity. This was alluded to before. And there is also going to be congestion on the grid, which means that there will be surplus energy that can be used and transformed into fuel or energy carriers. So we have the product ready. We are compatible with existing infrastructure. As a company, we now have demonstrated the solution and ready to scale up and deliver larger systems. And I think what is important also that we will stay competitive with other advanced fuel pathways. That is, transformation of biomass into fuel is going to be also quite expensive. And that is basically our target, to compete with those and be better. So thank you for listening.
Thank you very much, Benedikt, for your presentation. Very interesting. It has already prompted quite a few questions that you can see in the Q&A box. So if you, we will read out and get most of them answered towards the end. And well, now next on the list, we have Juergen Battke from ThyssenKrupp. So Juergen, over to you.
So, okay, now you should see my screen.
Yes, I can see
it. Okay. First, thank you for the opportunity to give this presentation about green methanol, which we think it's a path forward to replace fossil fuel. My name is Juergen Battke. You have my contact data here on the slides. You can download the slides later, I understood. So I would be happy if you stay in contact. And if anybody has some question, I would like to answer in writing, or give me a call, or we can answer all the questions now in this session. Okay, in this presentation, I would like give a short glance about ThyssenKrupp, my company. I want to explain the advantages of cooperation with ThyssenKrupp Industrial Solutions. I want to introduce the silicon fire technology for CO2-based green methanol plants. That means the combination of electrolysis and methanol synthesis based on CO2 and hydrogen. And then I have a last slide showing or providing an overview of our global references, which are the plants we have built the last 100 years. Okay, ThyssenKrupp itself is divided in business areas, and here in the blue box we have the business area of industrial solutions. This industrial solutions is responsible for chemical plant technologies and engineering, and we are quite big, so we have more than 21,000 employees globally. ThyssenKrupp as a whole has had a sales of more than 42 billion euro last year, and globally we have more than 160,000 employees in our network. ThyssenKrupp Industrial Solution, the business area itself, is subdivided in different business units, and you can see on this slide, and I put 4 business units in the upper line. It's the electrolysis technologies, it's the business unit for fertilizer and syngas technology, which is the owner and co-owner of the Swiss Liquid Future Methanol technology. Then we have the business unit of industrial specialties. They are dealing with gas cleaning technologies. And we have here the cement technologies. Why did I put these 4 business units in one line? It's just to give you an example that we could actually provide all solutions for projects related to green methanol. I'll give you an example. For instance, if you have a cement plant, and then our colleagues from the business unit cement technologies could convert this cement plant to an oxy-fuel process, and this cement plant then will produce flue gas very rich on carbon dioxide. Our colleagues from the business unit industrial specialties could further clean up this carbon dioxide, because the methanol synthesis needs a pure carbon dioxide. And of course, this oxy-fuel process needs pure oxygen, and this could be produced by the electrolyzer, and the electrolyzer, of course, is producing hydrogen too. And then we have everything complete. We have pure carbon dioxide, we have pure hydrogen, and we could convert it by our methanol synthesis, which is coming from the business unit fertilizer and syngas technologies. So this brings me to the advantages of the cooperation with ThyssenKrupp, because we think we are the right partner for a project, because we can provide solutions for all different phases of a project like building an methanol plant. We can deliver all kind of engineering. We can do the procurement for your project, and we also could deliver the C part, which is construction and commissioning. And it's not shown on this slide. We also would like to deliver the after-sales services, spare parts, training, but also assistance to operation of the plant. And even if it's requested, we could offer the operation of the plant itself. That means all the licenses, basic and detail engineering, the EP packages, or the full EPC execution is coming from one single source. And we can do that because we are the owner or the co-owner of the alkaline water electrolysis and the Swiss liquid future technology. So we have everything in place. That means there are no gaps between the different technologies. There are no interfaces with other third parties. And this allows us the shortest possible workflow so we can minimize the overall project schedule, and actually project duration means sometimes project money or project cost. Of course, we have a track record for delivery in time and in budget. So we are in a position to provide the full competence for all project phases. So we can start with very early project phases like the project development. We have a dedicated department for project development. Would be happy to support the customer to develop this project. We can prepare feasibility studies. We can elaborate basic engineering, detail engineering. We can do the procurement, construction of the plant. And I think that's pretty important. We also have a dedicated service business, so we can provide this after sales services and assistance during the plant operation or operation of the plant itself, build and operation. Now introducing our silicon fire technology for green methanol plants. And actually everything started with a business idea for small scale plants. The idea was, or one of the ideas was, that we want to store green power as a green fuel. And the green fuel should replace the fossil gasoline. For this particular project, we considered a decentralized production in direct proximity to the power plant substation. So we have no transmission losses and no transmission fees. The customer should get revenue from CO2 compensation. The production should be independent from oil and also independent from oil price cycles or fuel imports. And I think this is quite important, and that the production of methanol from hydrogen, which is coming from power, and carbon dioxide, should increase the economic of the new renewable power generation. For that, we have optimized our methanol synthesis for small and medium capacities. If I talk about small capacities, what is the meaning of small capacities here? I have put down 12 metric tons per day of methanol. That's about the size of the very nice plant of carbon recycle in Iceland. And this would correspond to an electrolyzer power consumption of about 5 megawatt. But of course, we are also targeting bigger capacities. We call it a medium capacity. For instance, something about 290 metric tons methanol per day, which would require about 120 megawatt electrolyzer. Having a look on this process scheme, we have here the different process units in the boxes, in the blue boxes. Everything starts with a water electrolysis. So we need power and water. The electrolyzer is producing hydrogen. This hydrogen is mixed with pure carbon dioxide. At least it should not contain, how shall I say, catalyst substances which may be toxic for the catalyst. The mixture of carbon dioxide and hydrogen we call feed gas. So we have to pressure up this feed gas to the operating pressure of the methanol synthesis. In this case, it's about 80 bar. And in the methanol synthesis, we are producing methanol and also water. That means we have two different phases. We have the gaseous phase, still containing some hydrogen and some carbon dioxide, though we are recycling this gaseous phase to the methanol synthesis. And we have the liquid phase, and the liquid phase is routed to a distillation. And for this small plant, we have now decided, or we are intending to have one distillation column because this is sufficient to upgrade the methanol to fuel grade methanol, which is actually about 99.5% purity or higher. In order to improve the economics of such a plant, we have modularized the process. And you can see on this sketch, the single modules are trackable, so we can pre-assemble them in the workshop, transport them easily to the site, and to connect them. And for the entire plant, we did the engineering. We have a first capacity template ready. It's in our drawer, so we can start with the project immediately. I want to close my presentation with a typical project characterization. It's a recent example of a small project in Europe. Of course, plant type, of course, is methanol from carbon dioxide and hydrogen. Technology will be our own technologies, silicon fire, methanol technology, and our alkaline water electrolysis. The production capacity, it's a small project, is 12 metric tons per day, fuel-grade methanol. And a typical scope of supply for these kind of projects is EPC lump sum turnkey. That means we are providing a fixed price and we're taking construction risk, etc. And due to our pre-configured plant concept, we have a very short implementation period. So we can start immediately if a customer wants to. And since we have our own plant layout engineering, so we can consider architectural necessities in protected landscapes, like in Sweden, like in Switzerland, wherever in Europe might be important. And what I like is we started with this project with a service agreement with temporary operation support, but the customer decided that he does not want to become a chemical plant operator. And so we are now negotiating a new agreement for full operation and maintenance. And this is a feedback from a lot of power producer. They do not want to become a plant operator. And so ThyssenKrupp is offering the full operation and maintenance services. However, we have learned that the economics of such a project strongly depend on local conditions. So we invite everybody that we have together a look on the site, that we identify the right site, and we can send our engineers to the site and then do a professional feasibility study, and then we can go step by step through the project development. Last slide, an overview of our plants we have built during the last 100 years. So we have built more than 2,000 plants. And next year we have 100-year anniversary in our company here at our site in Dortmund. So we have fertilizer plants on the left side. We have hydrogen, ammonia, methanol plants. And of course we have plenty plants for electrolysis and electrochemical technologies. Yeah, thank you very much for your attention, and I hope I can, or I would like to answer your question here in this session, or you can download these slides and you contact me directly by phone or by email. Thank you very much.
Thank you very much, Juergen, for your presentation. And you know, very rarely we get so many questions. So we have over 30 questions now. Yes. So, okay. You know, we'll. I can say with a degree of confidence that we won't be able to answer all of them, but we'll get through most of them, as many as we can. And then you're free to get in touch with you know, our speakers, and they will be able to answer. So yes. One question that I think is quite relevant is where do you see, in which parts of the world you see renewable methanol growing, and why? So perhaps you want to start, Juergen?
Okay, yes, of course. I think there will be plenty of different sites which are good for this kind of methanol plants. Either you have a carbon dioxide source, or you have plenty of cheap renewable energy. For instance, if you have a paper mill, you have a boiler, and this boiler is incinerating a biomass, and you get a pretty, how should I say, you get a flue gas with a high carbon dioxide concentration by regenerating the lye of this pull process, and of course this carbon dioxide is a good source for our methanol synthesis. So then we do not have to transport any CO2. But on the other hand, if it's necessary, for instance, for small projects, that we go direct proximity to a power plant, that we do not use the network, the transmission net, then it might make sense under certain conditions to transport the CO2 to the plant. So we would investigate each site and do a systematic analysis, and then we can calculate or we can evaluate, is it a proper site or not. But I think there will be plenty of sites in Europe and the rest of the world, of course.
Thank you very much. I don't know if Benedikt, if you would like to add anything, or Lawrence?
Sure, Carlos. I'd just add there that I think moving forward in the future, government legislation on emissions is going to play an important role in where these renewable methanol technology is most viable and cost competitive. Europe already has the RED2, and the it also has a number of other policies, such as the Fuel Quality Directive. In the U.S. right now, we have the Renewable Fuel Standard. We'd like to find a place for renewable methanol there as well. That's primarily corn ethanol based right now, but there's a lot of movement here, especially if you look at the marine sector. We have emissions control areas coming into effect all over the world, sulfur reductions. There is a proposed 50% reduction in greenhouse gas emissions in the marine sector by 2050. So these are all things that will, that will be drivers for renewable fuels and renewable methanol in particular.
Thank you, Lawrence. So Benedikt, I have a specific question for you. So they ask about the to compare Maxim Lyubovsky asks about the cost of renewable methanol versus regular methanol made from natural gas. Do you have some benchmark prices you could talk about?
Well, as I mentioned earlier, we are basically transforming one energy source into another. So it is fairly obvious that therefore there's no one single answer to that question, because it depends on the if we think about this in the context of renewable methanol with electrolysis, then it's then the power price is driving the economics. So all I can do is basically tell you that in the last few years that we've been producing and selling, we have on average been achieving prices that are approximately twice the price of the current fossil methanol at that time. And the benefit that you're receiving is essentially the reduction of CO2 that you can apply to any given mandate or quotas that you have to fulfill. And so therefore, this product can be traded at a much higher price than methanol from natural gas, which obviously has associated with it considerable amounts of CO2 emissions, both in the production process as well as in use, because you're introducing new CO2 into the atmosphere. So this is basically all driven by what is the market willing to pay, which is the comparator that you're looking at. As I mentioned in my talk, we are competing with other advanced renewable fuel processes where we are competitive, definitely. And the benefit that we are delivering cannot be delivered by anybody who is producing from natural gas, because then you're not producing a renewable fuel at all.
Thank you very much, Benedikt. I don't know if any of the other speakers would like to add to this question.
Yeah, if it comes to different, how should I say, sites which may be interesting, I want to give a reference. For instance, if you want have a look in the internet, for instance, my company built the so-called carbon to chem project. It is located at a steel mill, our ThyssenKrupp steel mill here in Duisburg. So we are taking the off gases from the steel mill and from the coke oven and clean it up and then route it to methanol synthesis. But we also have test facilities for a lot of other liquid fuels, and we have also installed an electrolyzer, and everybody is invited to visit this site. You can easily find in the internet.
Thank you very much, Juergen. So one question that goes to the heart of this webinar. So how to deal with intermittency with energy storage. So very briefly, so how could you use renewable? How could you harness excess renewables that are, you know, a feature of intermittent energy sources to produce renewable methanol?
If I may just jump in first. What we have done in our development is to basically ensure that the whole system can work with intermittent energy sources. So normally when people design chemical plants, they are designed to run base load continuously, and it's very difficult to take 1 or 2 or 3 modules offline because they are all quite interlinked. In our case, the process is highly modular. The CO2 capture, the electrolysis, and the downstream are fairly independent systems. And also the chemical system is designed so that it can accommodate very low turn down. So when the electrolyzers have to go offline for some reason or have to go on a low turn down, then the chemical system can easily adapt. This is also one of the reasons why we were granted money from the Horizon 2020 funds to install a unit in Germany, which I mentioned in my presentation. There we're going to take basically the load profile in real time for wind energy in Germany and drive our process based on that. So we will be entirely dependent on the availability of wind energy at any given time during the while we're running the plant. And electrolyzers, we have good experience with alkaline electrolyzers, which are what people consider now to be the trusted and vintage process. We know that they can respond quite well to fluctuations in electricity availability and can work on low turn down as well. So the whole system is designed with that in mind.
Thank you very much, Benedikt. Anything to add, Juergen or Lawrence?
Yes, of course, Benedikt is right. It's good that the alkaline electrolyzer can follow the spot market, whatever, is quite flexible, and also the methanol synthesis. But I think a next step could be that we identify the right site. For instance, I'm visualizing a big industrial site, and which is having a cavern underneath, and this cavern could be easily used, could be used as a storage for the hydrogen. That means the electrolyzer is producing intermittently hydrogen, but then the downstream synthesis can run on flat rate, and this is improving the economics. So there are a lot of possibilities. So actually we are free.
Thank you very much, Juergen. So I have another question that I think makes a lot of sense. So as I'm fairly sure that all of you who are here with us know, one of the ways to make methanol is to well, you need hydrogen to make methanol. So why don't you use hydrogen as a fuel if you already if it's part of a process? So what is the advantage of using methanol in energy uses over using hydrogen?
Well, I can jump in if I may. I think it's quite obvious that we have been using liquid fuels in transport systems now for well over 100 years because of their advantages. They are easily stored, they're easily transported, they are fairly energy dense per unit of volume or unit of weight. If you compare that then to hydrogen, you know, it carries a very low amount of energy per volume. In fact, in 1 liter of methanol, which is totally uncompressed and just liquid at atmospheric pressure, you have more hydrogen than you have in 1 liter of hydrogen after you compress it up to 800 bars or so. So after you compress it to 800 bars, you've already spent a lot of energy on that. Then you have to use specialized tanks, both in the transport and storage. In fact, this is what people are struggling with when they're designing future system based on hydrogen. Is you know, where are you going to produce the hydrogen? You have to bring in a lot of energy for that, or if you have a distributed system, you have to now empower fuel stations to have very high amounts of electricity. And then in the cars, you have to have compression systems which weigh a lot and are difficult to maintain and so on. And of course all the infrastructure has to be replaced essentially to accommodate the new fuel source. While you know, we have good experience, of course, with using methanol in blending or as a pure fuel with existing pumps and infrastructure.
Thank you very much, Benedikt. So we still have a number of questions here. In fact, 34 questions. The number hasn't gone down at all. So one of the questions I think is very interesting, at least from a technical point of view, is whether your a plant that uses makes renewable methanol from intermittent energy sources, whether it would have to be designed to start up quickly and shut down and restart again. Is this how the process works, or do you have a way of keeping the plant running for most of the time and then use intermittent energy that would be curtailed otherwise when available? I don't know who wants to go, Benedikt.
Well, I can, you know, we have practical experience with this. First of all, as I mentioned earlier, we are designing the system to be very flexible to load in general. Of course, what we would like to do is to basically keep the reaction system so that it doesn't go completely cold, because that startup then from cold start to warm again can take hours. While if you have a low amount of energy available that you can use to keep your the catalysis system, the reactor warm, you are very able to basically flex the system going up and down quite rapidly. And you know, we also deploy or employ a small buffer tank for hydrogen, which you know, can help, and so on. You know, the issue is, of course, that from cold start to warm takes some time, but if you have energy available to keep your system at a fairly stable, so it doesn't need the hydrogen or the CO2 to come in, but just you keep your system warm, you're very flexible up and down in the chemical system. And the electrolysis, of course, is another matter. I mean, electrolyzers today, even alkaline electrolyzers, are designed to be able to go up very rapidly and down very rapidly.
Okay, thank you very much, Benedikt. So going more to the market side of these topics. So Jonathan Walters posed a question that says, are you worried that the current politics of international trade protectionism could undermine your business model? Any thoughts on this question?
Well, I think that's the, I mean, obviously what we are doing right now is that we're entering a new era in which we need more advanced renewable fuels instead of the crop-based biofuels. So we'll see a lot of changes in the next few years. The market has since here in Europe since 2009, and even well before that in the US, when US started using large amounts of ethanol, has been dominated by crop-based production, primarily ethanol from corn and biodiesel from oilseeds and palm oil and soy. The EU has been, of course, in a battle with imported palm oil, imported soy, biodiesel, and so on. And it's difficult to predict exactly what happens on that front, but generally speaking, those products are now going to be under pressure because they are crop-based. So we will see more competition from, especially within the region, with waste products, waste biomass, as well as these new technologies that are based on electrolysis.
Thank you very much, Benedikt. Quite a comprehensive answer. So also more of a technical question, I suppose. So what is the energy balance of this process? I don't know if this is one of those questions that could be answered straight. I think it probably depends on the inputs you put in, but I'll leave it to the experts to attempt to answer it.
Yeah, so I gave that answer really on the slide that was at the back of my presentation. Essentially what I'm assuming there is that to make 1 ton of methanol, I will require 11.25 megawatt hours of electricity. That is from end to end. That is for the electrolysis and the compression of the hydrogen up to the right pressure for the catalysis or for the reaction. We also need a small amount of heat energy, which can come actually from waste heat from the reactor mostly for the distillation process. And the driver here is the electricity. And so if you calculate that into basic efficiency, it's about 50%. 50% of the electricity gets converted into chemical energy, lower heating value. The electrolyzers then can be improving in the coming years somewhat. They haven't quite come to their limit. Some people strongly believe, for example, in solid oxide electrolysis, which requires some source of waste heat that is coming from an external source. Therefore, you can show more overall efficiency with that technology. But basically, at the moment, what I'm giving you is sort of a reference number for the state of the art in electrolysis.
Right. Well, thank you. Thank you very much. I'm afraid that we are getting towards the end of the webinar. So I would like to bring this to a close and thank all of you who have been with us, watching the presentations and posting so many questions. I know that Juergen and Benedikt have already said that they will attempt to answer as many as possible if you reach out by email. So thank you very much for being here. Juergen, could you stop sharing the presentation so we could put the closing slide if you stop sharing your screen? And then I don't know whether you'd like to say a few words, Benedikt, as a way of goodbye.
Yes, I just want to thank you all for listening and thank you for this opportunity to talk about this very important topic. As I mentioned, we are a company in the business of developing these systems and selling renewable methanol. So of course, please feel free to contact us with any further questions. And again, have a good day and thank you for being here.
Thank you very much. Juergen, any parting words?
I'm struggling to switch out my presentation. I'm sorry for that. Thank you for the opportunity. It was much fun. So it's the first time I took part at a webinar. I think it's a dear. I wish you much success in the future, and thank you very much for your colleagues. Thank you to Benedikt and to Lorenz. Very interesting for me, and I wish all of the audience a nice day. Thanks.
Thank you very much, Juergen. Larry?
Hi, thank you, Carlos. Thank you, Juergen. Thank you, Benedikt. I think this has been a great webinar. Thank you to all the participants for the wonderful questions and the engagement. And primarily, thank you, Carlos, to you and ATA, Araceli, and everybody else who was involved in putting this together and making it work. We very much appreciate it. And to the participants, as I said, thank you. And please don't hesitate to reach out to us. We'll be happy to answer any questions and would love to speak with you further. Thank you.
Thank you very much, Lawrence. So, well, thank you once again for being here with us. And remember that you could always attend our webinars. You could find all of them at atainsights.com. And you will, I have seen this question a few times, you will definitely get the presentations and you'll be able to see the webinar recording as well. So see you next time and have a good day. Bye.